When calculating for equilibrium values, sometimes the math is simple, but majority of the time the math gets more complicated, especially if the numbers are very large or very small. When we use the 5% rule, it simplifies the math because x or 2x becomes negligible. That means if I add by x or if I subtract by x, the final answer will not change. Therefore, we could ignore x. In addition, two other criteria should be met. Number one, k, the equilibrium constant, should be less than 1. In general, k should be about 10 to the third times smaller than the initial concentration of what is given. Lastly, you must check to see if the 5% rule is valid. So that is x, whatever value that you solve for, divided by the initial concentration given, times 100 must be less or equal than 5%. If that is true, then this is valid. If it is greater than 5%, you must redo the math. So let's look at the following reaction. It begins with N2O4 with the initial concentration of 1.00 molar. Its equilibrium constant is 4.46 times 10 to the negative third. It says determine the equilibrium values. Initial was given. You are looking for the equilibrium values. First thing I need to do is set up an ICE table. So N2O4, 2NO2, ICNE. The initial concentration is 1.00 molar. This is 0 minus x plus 2x. Equilibrium is the addition of IC, so it's 1.00 minus x, 2x. Here I just rewrote the values in the previous slide in a table format so it's easier for you to see. We're looking for x because we want to find the equilibrium concentration. So first thing I need to do is write my equilibrium expression, which is K EQ is equal to NO2 squared divided by N2O4. So plugging my values in, it's going to be 2x squared divided by 1.00 minus x. This is going to be equal to 4.46 times 10 to the negative third. So now I'm going to cross multiply like this. So that's going to be 2x squared is equal to 1.00 minus x times 4.46 times 10 to the negative third. And I'm going to square the left side, so that becomes 4x squared. And I'm going to distribute on the right side. So this is going to be multiplied with x, and this will also be multiplied by 1. That becomes 4.46 times 10 to the negative third minus 4.46 times 10 to the negative third x. Now I'm going to move everything to the left side to make it set it equal to 0. So that's 4x squared plus 4.46 times 10 to the negative third x minus 4.46 times 10 to the negative third equals to 0. So now we have a quadratic equation. So when you plug it into the quadratic equation, remember quadratic is x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So if I plug this in, this is negative b, which is 4.46 times 10 to the negative third, plus or minus square root of b squared, which is going to be 4.46 times 10 to the negative third squared, minus 4, a is 4, c is 4.46 times 10 to the negative third, divided by 2 times 4, which is the a. Plugging in, you get two possible answers, 0.03284 or negative 0.03284. 0.3395. One of the choices is negative. The positive answer is correct. Now we're going to repeat the problem using the 5% rule. The 5% rule begins with the same equation, which is 2x squared over 1 minus x. This is equal to 4.46 times 10 to the negative third. Here we are able to eliminate my x. We say the x is so small, it's going to approach 0. So no matter what value of that x is, it is so small. When I subtract from 1, it is going to equal to 1. So my equation now becomes 2x squared over 1 equals to 4.46 times 10 to the negative third. So this becomes 4x squared is equal to 4.46 times 10 to the negative third. I divide both sides by 4, and the 4's on the left cancel out. And then I take the square root of both sides. X is equal to 0.0334. So now, after you apply the 5% rule, you must always check to see if it's valid. So my check is going to be x over initial concentration times 100. So my x we calculated as 0.0334 divided by my initial concentration, which was 1.00, times 100. This equals to 3.34%. So this is valid because it's less than 5%. So for this problem, we did not have to apply the quadratic equation. Eliminated x because x approached 0. We could have made the math simpler by applying the 5% rule and stated that x approaches 0. And as you can see, we solved it both ways, and the answers are very similar. So to find the equilibrium concentration, we just plug it back in. We have N2O4 is equal to 1.000 minus x. That's going to be 1.000 minus 0.0334, which equals to 0.9666. And then we stated NO2 was equal to 2x, so that's going to be 2 times 0.0334, which equals to 0.0668, both in units of molar because they are in concentration. Pause the video and solve this problem on your own, and then check your answer. Use the 5% rule. There is a part A and a part B. Phosgene decomposes by COCl to CO plus Cl2. The equilibrium constant is given as 8.3 times 10 to the negative 4 at 360 degrees. Calculate the equilibrium of each species in the 10-liter flask. A at 5 moles of COCl2 and B at 0.100 moles of COCl2. Since this is not at equilibrium because it's decomposing, we have our initial concentration. So we're going to start with our ice table, COCl2. So my ice table will start with my initial concentration, which will be 5 moles divided by 10 liters. I have 0 initial concentration for CO and Cl2. My change in is going to be minus X on my reactants plus X on my products. So my equilibrium is the addition of I and C. So this is going to be 0.5 minus X plus X plus X. This is for A, but B is exactly the same except for my initial will be 0.1 over 10. So I just reorganized the table. And now we're going to write our KEQ equation. So KEQ is going to equal to CO Cl2 divided by CO Cl2. And now I'm going to plug in my equilibrium values, which is x times x over 0.5 minus x. This is equal to the given equilibrium constant, which is 8.3 times 10 to the negative fourth. We're going to apply the 5% rule, which means the value of x is so small that when I subtract from 0.5, it's going to equal to 0.5. So this is going to approach 0, so we can ignore it. So if I simplify, this is x squared. I'm going to move the 0.5 to the opposite side. So this is 8.3 times 10 to the negative fourth. And then I need to square root after I multiply. So x equals to 2.0 times 10 to the negative 2. So now I'm going to check to see if this value is valid using the 5% rule. So 5% rule states that concentration of x over the initial concentration times 100 has to be less or equal to 5. So now I'm going to plug in. So x is 2.0 times 10 to the negative 2 molar. Initial concentration was 0.5 molar times 100. This equals to approximately 4%. So this is valid because it's less than 5%. So our concentrations at equilibrium, COCl2 is equal to 0.5 minus x. So this is going to be 0.5 minus 2.0 times 10 to the negative 2 equals to 7.5 times 10 to the negative third molar. CO equals to Cl2 is equal to x, and so x is equal to 2.0 times 10 to the negative 2 molar. So we're doing part B. The setup is exactly the same except for the initial concentration is 0.10 mole per 10 liter. So we're going to write our equation again. Equation is going to be KEQ is equal to CO times Cl2 over COCl2. Plugging our values in. This is x times x, 0.01 minus x. This is going to equal to the equilibrium constant, which is 8.3 times 10 to the negative fourth, and that was given to you. We're going to assume the 5% rule again. So that means x is so small, 0.01 minus x will equal to just 0.01, so we could ignore the x. So this equation becomes x squared is equal to 0.01 cross multiplying times 8.3 times 10 to the negative fourth, square root. So x becomes 2.9 times 10 to the negative third. Since we applied the 5% rule, we need to check if the 5% rule is valid. So the concentration of x over the initial times 100 has to be less or equal than 5%. X is 2.9 times 10 to the negative third divided by 0.01 times 100. This equals 29%. So we cannot use the 5% rule in this case. This is why you must always check if the 5% rule is valid. So that means we need to solve this using the quadratic equation. Starting from up here, use the quadratic equation. So this is going to be x squared over 0.01 minus x equals to 8.3 times 10 to the negative fourth. And cross multiply, so this is x squared is equal to 0.01 minus x times 8.3 times 10 to the negative fourth. Now I need to distribute this to the x and then to the 0.1. X squared is equal to 8.3 times 10 to the negative sixth minus 8.3 times 10 to the negative fourth x. Now I move everything to the left to make it set equal to 0. So x squared plus 8.3 times 10 to the negative 4x minus 8.3 times 10 to the negative 6 equals to 0. Quadratic equation, x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. Plugging it in, this is going to be negative 8.3 times 10 to the negative 4th plus or minus square root of 8.3 times 10 to the negative 4 squared minus 4. A is 1 and C is 8.3 times 10 to the negative 6 divided by 2 times 1. Solving for x, you get 2.5 times 10 to the negative 3rd and negative 0.00333257. So we know that. So the negative answer is wrong. So this is my correct answer. So now we need to find the equilibrium concentration. CO equal to Cl2, which is equal to x. So this is going to be equal to 2.5 times 10 to the negative 3rd molar. COCl2 is equal to 0.100 minus 0.0100 minus x. That's going to be 0.0100 minus 2.5 times 10 to the negative 3rd molar. This is going to equal to 7.5 times 10 to the negative 3rd molar. When using the 5% rule, you must always check to see if it's valid. It is always x divided by the initial concentration times 100. The validity only works for less than or equal to 5%. If it is not valid, then you must redo the problem using the quadratic equation or the square roots of the squares. Pause the video, try this problem on your own, and then check your answer. Calculate the equilibrium concentration for the reaction below if the initial N2 equals to 0.8 molar, O2 is 0.2 molar. So already you know you have to create an ICE table. So ICE initial was given as 0.80 molar for N2 and O2 is 0.20 molar and this is equal to 0. So the change is minus x plus 2x. Equilibrium is the addition of the 2. So 0.0 minus x, 0.20 minus x, 2x. So above is the table. So we're going to write the equilibrium equation, which is KEQ equals to NO squared over N2. So plugging in, it is 2x squared over 0.80 minus x, 0.20 minus x. This is going to equal to 1.0 times 10 to the negative 5th. So we're going to apply the 5% rule. When we apply the 5% rule, we say the x values are so small that if I subtract 0.8 minus x, it is 0.8. And if I subtract 0.2 minus x, it is 0.2. Simplifying, this is 4x squared, 0.8 times 0.2 equals to 1.0 times 10 to the negative 5th. So cross multiply. So this becomes 4x squared is equal to 0.8 times 0.2 times 1.0 times 10 to the negative 5th. Divide both sides by 4. The 4's cancel out and take the square root. So x equals to 6.3 times 10 to the negative 4th molar. Now solving for the equilibrium values for each one. Now we're going to check to see if the 5% rule is valid. So that's going to be concentration of x divided by initial concentration times 100. So this is going to be 6.3 times 10 to the negative fourth molar over, and here we have two concentration initial, and they are not the same. One is 0.8 and one is 0.2. So the initial concentration we want to check for is the smaller one, because if it works for the smaller concentration, or if it's valid for the smaller concentration, it will be valid for the larger concentration. Times 100. This equals to 0.315%. So this is valid. It is less than 5%. N2 is equal to 0.8 minus x. This becomes 0.8 minus 6.3 times 10 to the negative fourth molar. So this equals 0.80. Do you see how if I subtract a small number, which x was, from a bigger number, it is 0.8. This is why we are able to make the 5% rule assumption. So for O2, it was 0.2 minus x, so 0.2 minus 6.3 times 10 to the negative 4 molar. This is equal to 0.2 molar. And again here, 2. The x is small again, so if I subtract from 0.2, it is 0.2. And then we need to find the equilibrium for NO. This is equal to 2x, so this is going to be 2 times 6.3 times 10 to the negative fourth molar equals to 1.3 times 10 to the negative 2 molar. The 5% rule makes the math a lot easier by eliminating x. We could eliminate x because the x is so small that when I subtract from another number, it is the number that we are subtracting from. After using the 5% rule, you must check if it is valid by taking the x concentration divided by the initial concentration. If more than one initial concentration is given, you want to use the smaller one, because if it's valid for the smaller one, it will be valid for the larger concentration. Remember, the 5% rule only applies if it is less than or equal to 5%. If it is not, you cannot apply the 5% rule. Therefore, you need to do the math as is. The general hint to use the 5% rule is the K valued, the equilibrium constant, concentration given, their difference must be bigger than 1,000.